2/3 heads and 1/3 tails for the coin is because you have prior knowledge about coin tossing. You assume that unless told otherwise, you want to believe that the coins are fair. And you should be pulled, screaming and kicking, to be made to believe that the coin is not fair. So one way of thinking about it is, even though you have the training data, you also assume that you have a whole bunch of virtual examples. So you're sort of believing that, Rao is tossing coin 3 times, but before he even started tossing these 3 coins, I've already tossed coins 100 times before. In those 100 times, I got heads 50 times, tails 50 times. So I have 100 virtual examples that I only know, Rao doesn't know. Plus then Rao has 3 more examples. In my 100 virtual examples, 50 came heads. In Rao's 3 examples, 2 came heads. So my count now would be 52 by 103. This will make sure that you will get, in this case, it's close to half. Whereas if Rao has no work and does 3 billion here, and this is 2 billion, then it will be 2 billion 50 by 3 billion 100, which will still be 2/3. This is what we will do. We will essentially assume the smoothing that we will use, what we'll assume is there are m virtual examples, and you need to assume, you have 100 virtual examples, you need to assume how many of them will come heads. Okay? I will just assume that uniform probability, if it can come either heads or tails, then I'll assume it will come uniform probability heads or tails. Okay? So then I will say I have, apart from the number of examples that Rao has, and number of those examples which have the attribute having a specific value, I also made up m virtual examples, of which m times p of them are actually also having a equal to bi. Now this p would depend on, if the attribute has 15 possible values, p would be 1 over 15. That's like assuming all values are equally plausible. Okay? If I do this, then essentially I will make sure that I am not blindly believing in the data. When the data is small, my prior should make a difference. But when the data becomes bigger and bigger, if you still continue to say, so in the beginning you may have you may have your own prior and you assume that this must be noise. But after 3 billion, you still want to stick to your prior, then you are being irrational. And this idea of what's called Laplacian smoothing, which basically allows virtual samples, which are added both to the denominator and numerator, will take care of it. So that's what you wind up doing in NBC. So that, in fact, it's done for all probabilities. Just not, this way you'll make sure you'll never get any zeros. But more importantly, all probabilities are going to be different now, because they're not just 2 by 3, it's 2 plus 50 by 3 plus 100. Okay? And as the number of training examples keeps increasing, the effect of this prior slowly wears away. And for the small number of training examples, the prior will basically make sure that you don't rashly jump to conclusions just because you saw a couple of examples. If you do that in computing your probabilities, then Bayes classifier works very well. Okay? I'll stop here. Next class, we'll complete this discussion and go into